Okay, so in this video we're going to talk about distances from point to a line, point to a plane, and from a line to a line. Okay, so first we're going to look at distance from a point to a line in 2 dimensions. So you may recall that in grade 10 you had a method for doing this where you had to find the equation of the line that was perpendicular to the given line and find the intersection point and then the distance between 2 points. Well, there's a method that is much shorter, but you need to understand vectors in order to come up with that. Okay, so first we're going to draw this diagram, or show you the diagram here. Already drawn it. And we're going to look at the line that's given. So line L here is given, so AX plus BY plus C equals 0. Okay, so that's in 2 dimensions. And we're going to call the distance here D from the point to the line. And the distance is going to be a perpendicular distance, because that would be the shortest distance that we're talking about. There's some point P naught on the line, let's call it X naught, Y naught. And some point, well, this is the point that you want to find the distance from, which is X1, Y1. And here's a normal to the line. Normal is AB. Okay, so we draw it there. We could have drawn it at the origin, but we're going to stick it here for convenience. And we've got this vector P naught, P1. If we project P naught, P1 onto the normal, we're going to get a vector that's length is equal to the distance that we're looking for. So we're going to look for the absolute value of the scalar projection of P naught, P1 onto the normal. Okay, so if we look at the projection, it's the normal component basically of this vector P1 or P naught, P1. Okay, so call it the formula for scalar projection is this here. Okay, so the scalar projection is the dot product of the 2 vectors, P naught, P1, dot onto n, and then you divide it by the magnitude of n. And this makes sense because the dot product P naught, P1 with n is the length of P naught, P1 in the direction of n times the length of n. So you're multiplying this number here, from if this is 0, so this number times the length of n. If you divide that by the length of n, then you're going to get this number back. Okay, so dividing it by the magnitude of n gets you the projection. Okay, so P naught, P1 is this. These are the coordinates of it. And by plugging it into this formula, x1 minus x naught, y1 minus y naught, dot AB, and over the magnitude of n is this. Complete that out, complete multiplying that out, and you end up with this nice formula here. Okay? So just doing the dot product of those coordinates up top, you rearrange it, you get AX1 plus BY1 minus AX naught minus BY naught. So if you have to pause to make sure that you got this, then that's okay. So we want to know what this is, though. Well, if you remember the creation of this formula, this ended up being a constant. Let's check it out. We know that P naught is on the line. So that means that AX naught plus BY naught plus C equals 0. It satisfies that equation. So if it satisfies that equation, then we can just rearrange it and we get C equal to negative AX naught minus BY naught. Which is that? So that's got to be C then. Okay? And we can then write the distance formula as this: AX1 plus BY1 plus C over the magnitude of the normal. Absolute value because the distance is positive. Okay. An example with that, well, let's just look at this quick one here. So take the line 2x minus y minus 1 equals 0 and the point 4, 8. Plug 4 and 8 into x and y into this formula. Don't forget the c value there. Divide it by the magnitude of the normal, which is 2, negative 1. And you get 1 over root 5 as the distance. Okay, so we've got that now. What about the distance from a point to a plane? This is very similar. So if we take a look at this picture here, we've got a point P1 here, a point on the plane P0. The distance from P1 to the plane is going to be a perpendicular distance. Call that small d because we're going to have a capital D in the formula for the equation of the plane. Okay, so now we've got P0, P1. We're going to project that onto the normal again. So the normal is ABC this time. The normal may be longer or shorter than this distance. May go even in the opposite direction. But still the projection, the scalar projection, will give us that distance. Okay, P0, P1 is this. So we're going to go through the same calculations pretty much and end up with a very, very similar situation. Okay, so P0, P1 dot n over magnitude of n. Same thing, we're just adding an extra coordinate. Okay. And when you've done that, you get this formula here. And again, this equals d because ax, x naught, y naught, z naught satisfies the equation of the plane. Okay? So we can substitute that constant in as d. And now we've got the distance from a point to a plane formula, which is right here. And a little example for distance from a point to a plane. Well, let's try this here. 3x minus 4y plus 7z minus 5 equals 0. The point's 3, 2, 1. Well, we're just going to sub these values in for the x, y, and z and divide by the normal, the magnitude of the normal. Plugging them in, we get these values, and we get the distance is 3 over root 74. Okay, so now we've got the distance from a point to a line in 2 dimensions, a point to a plane in 3 dimensions, and now we're going to look at a point to a line in 3 dimensions, which is more complicated. Okay? So let's look at this here. So distance from a point to a line in R3, well, we need to draw the diagram. Okay? Here's the point P1. Here's the line. Some point P0 on the line, which you can get from the parametric equation or vector equation from the line. And you want to find this distance here, this perpendicular distance to the line. Well, the direction vector can be written here. We know that the cross product of P0, P1, and M will give you the area of the parallelogram formed. If we can get the magnitude of that cross product. If we can get the magnitude of that cross product and divide it by its base, okay, so the area of a parallelogram is the base times the height, so the base times the height, so d is the height. Well, then we've got this. The area of the parallelogram is the magnitude of the cross product. The base is the magnitude of m, and d is the height. Rearrange this, divide both sides by m, and you've got the distance from the point to that line is this formula right here. Okay, let's try this out. So we've got an example here. Here's a line, parametric form, here's a point. We're going to do P0, P1, so P0, P in this case, is going to be this, 0, 1, negative 6. Okay, so here is P0 from this part here. That gives you P0. So P0, P would give you this vector. M is 2, negative 1, 5, 2, negative 1, 5. Okay, I'm going to plug it into the formula. Cross product those two vectors, divide by the magnitude of m. When you've done that, you get this part here, so you take the magnitude of that vector on top, you get that, and the answer for that one is root 149 over 30. Okay, so that's the distance from a point to a line in 3 dimensions. Okay. Now the distance between two skew lines. So two skew lines in space. Well, let's just take these two lines here and see. This is a bit of an application of what we're doing. So let's take these two lines here. Well, I'm going to draw a picture. I'm going to show you a picture here with those two lines in it. They're skew, but you can create two planes that are parallel that contain those two lines. So by creating one plane is enough. Use a direction vector from this line and this line to create another direction vector for this one to get that plane. Okay. Once you've got the equation of this plane, pick any point on this line, find the distance from that point to that plane, and it's equivalent to the shortest distance between the two skew lines. Okay. So here's an example, or the continued example. Let's take the equation of this plane here. I'm using the second plane. So we've got the equation of the line plus the other direction vector. Convert to Cartesian form. We're going to cross product the two direction vectors to get the normal. Okay. So cross product the two direction vectors to get the normal. Plug that into the Cartesian equation. Solve for d by plugging in the point. Get d equal to -84, and we get this as our Cartesian equation of that plane. Now we can just use the formula for the distance from a point to a plane, using a point on the original first line to the plane containing the second line that it's parallel to. Okay, so here we go, and we've got the distance d equals the distance from the point on R1. So 1, 2, 3 to the plane that we created. Plug it in. We get 80 over root 659. Okay.